In the last lecture, we discussed about the application of statistics in quality control. Now today, this lecture is very focused on one technique called acceptance sampling, which makes use of probability and statistics. So what is acceptance sampling? Acceptance sampling involves evaluating a portion of the product in a lot for the purpose of accepting or rejecting the entire lot as either conforming or not conforming to quality specifications. So what is done in this, that we have got a lot may contain lot of items, maybe 5,000 items. It may not be practical to inspect all 5,000 items. So we just take some items, maybe 100 items, and inspect them. If the quality is found okay, then we accept the whole lot, and if we find many defects in the sample, then we reject the lot. So another example is that while purchasing food grains, the usual procedure is to take a handful of the grains in our hand and inspecting its quality on the basis of size, color, odor and texture. So that's what we do. That if that handful of grains is found good, we decide to purchase the grains. However, if we are not satisfied, we inspect another handful of a different grain and repeat the procedure. So the handful of grains represents the sample on which inspection is carried to determine its acceptability. So then in that case, handful grain becomes a sample. The different types of grains represent the lot. Okay, so maybe that we have got 4 farmers and they have brought food grain to you. So you take one handful of grain from each farmer's bag and see the quality. So each farmer's bag is called lot, and then you have taken the sample out of that, and based on the sample you will be taking decision. So now there are 2 types of acceptance sampling. One is the acceptance sampling by attributes, okay, and other is the acceptance sampling by variables. So let us discuss first acceptance sampling by attribute. Here attributes refer to characteristics that are either present or absent, or that can be classified as conforming or non-conforming rather than being measured on a continuous scale. So it is an example by attribute is that, suppose you have taken some items and you just decide whether it is defective or not defective based on any things. So you are not having that any continuous variable, either the object or item gets passed or it does not get passed. The statistical method used to decide the acceptance or rejection of lots is provided by a curve. We make a curve to make that. This curve, called operating characteristic curve, is a graph of fraction defective in a lot against the probability of acceptance. What we will do that, suppose in the lot there is some percentage of defective items is there. Let us say we have a lot of 1000 and 1% item is defective. That means in 1000, 10 items will be defective. Then we can find out that if we make some sampling plan, we may make some sampling plan like we will inspect 100 pieces, and if there will be 0 defect, at most 1 defect, we will accept that. Otherwise, we will reject that. Suppose we make some type of plan, then we can calculate that given 1% defective in the lot, whether what is the probability that this will be accepted. So like that we can make a curve that if we have got different type of percentage defective, sometimes you have 1% for 2%, 3%, 0.5% defective. If you have such type of lot and if you make a sampling plan, say that inspecting only 100 samples and passing it, if the defect is less or equal to 1, then what is the corresponding probabilities? Okay. So such type of curve we can plot, so that both manufacturer and purchaser, they know that what is the probability, because ultimately it is based on the probability. So therefore both agree to that type of plan, and then they can take a decision that this should be done. So that curve is called operating characteristic curve. Now let us see the terminology. If we use capital N is equal to lot size, small n is equal to sample size, say lot size may be 1000, sample size may be 100, and C is the number of defective items in the sample permitted. That means how many defective item I can permit, that is called acceptance number also. PA is the probability of acceptance, that I can calculate by mathematics, by probability theory. And P is the fraction or percentage defective in the lot. So variable C is called the acceptance number of defectives. Thus the value of C is equal to 2 means that if number of defectives are 0, that means no defectives, 1 or 2, the lot would be considered acceptable based on the sample only. I just inspected 100 components and found that defectives are only 2. So we said okay, it is pass. If defective is 3, then we will say that no, whole lot will be rejected. So if more than 2 defectives are found, the lot would be rejected. So how to construct that operating characteristic curve, that means probability versus how much is percentage defective. That curve is essential so that you understand what is happening. So let n is equal to 1000 and small n is equal to 60, that means lot size is 1000 item, sample size is 60, and let us say C is equal to 3, acceptance number is 3, that means in 60 even if we find 3 defectives we can pass, and let us say P is equal to 0.01, that means actual fractional defective is 0.01, that means out of 1000 there will be defectives, so there will be 10 defectives there in the lot. So above sampling plan means that one should take a random sample of 60 from a lot of 1000 items. This is also important that the sample should be totally random. If the sample contains more than 3 defectives, reject the lot, otherwise accept it. So the value of probability of acceptance is calculated using the Poisson's formula. We can use binomial formula also, but in this case Poisson formula is appropriate, particularly if the, let us say n is large, around maybe 60, 100, that type of range is okay, and P is very small. In that case Poisson distribution also gives proper result. So Poisson distribution formula is this. This is the formula. P probability of acceptance are given, that something like that we can say probability that there will be C defectives, that will be given by n into P to the power C into E minus exponential to the power minus n into P and divided by factorial C. This is the formula that if you have this much fraction of defectives like P is equal to 0.01 here, in that case what is the probability that there will be 0 defect? Then in place of C you put 0. What is the probability that there will be 1 defect? In place of C you put 1. What is the probability that there will be 2 defects? Put C is equal to 2. So that means this will give the probability. So naturally the probability of acceptance will be sum of 3 cases, that case 1 when there is a 0 defect, and case 2 there is only 1 defect, case 2 there is 2 defects, and case 3 means 3 defects, and sum all these probabilities you will get the probability of acceptance by this scheme. So percent defective in a sample of size 60 is 0.01. In fact fractional defective rather, it can be expressed in percentage also. Percentage means 1%. So suppose you have fractional defective at 0.01 into 100, that means this is 1%. Okay. So this is something, this can be precisely, this is fractional defective. So fractional defective, fractional fractional defective. So this is equal to, in a sample of size 60, 0.01 and the value C is 3, that means acceptance probability, then the probability of its acceptance, rather this one is the probability that there will be 3 defects in the sample. So this is given by this one 60, because sample size is 60 multiplied by 0.01. So fractional defective is 0.01. In a way, NP means something like that. On an average, there will be 0.6 defects and to the power 3, because this is 3. So this 3 goes here, 3, and E minus 60 into 0.01. So this is only always 60 into 0.01 divided by factorial 3. So this becomes 0.0198. That means that probability is very small. Similarly, if I want to find out PA2, what I will do, that if I want to find PO2, I can say 2, and this becomes only, I have to make change 2 here, and this becomes 2. So that means this will be PA2, and then this quantity will be calculated, and this comes 0.0988. Put that value. So then I want to find out what is the probability that there will be 1 defective. So we just have to say that, here instead of 2 we will put 1 in the formula. We say 1 here, we say 1 here, power 1, and this is factorial 1, of course this one. So this will also go, and this will come, if you calculate, you will get 0.3293. Okay, e to the power minus 60 into 0.01, no change here, this will always remain. And if you talk PA0, so we cut this thing, so what we do here, that we cut PA0, instead of 3 we put 0, means probability that there will not be any defect in my sample, although on an average it is expected to, statistically it is expected to have 0.6 defect, but 0, so that means put it 0 here. So 60 into 0.01 whole to the power 0 is 1, and this is 0 factorial. So 0 factorial is also 1, and this if you calculate, it will come 0.5488. Okay, so that probability comes 0.5488. So you got PA3 also, that is 0.0198, PA2 also you got, PA1 also you got, PA0 also you got. PA means precisely, PA doesn't mean acceptance, rather PA means that what is the probability that there will be 0 defect, what is the probability that there will be 1 defect. So overall probability of acceptance is PA3 plus PA2 plus PA1 plus PA0, because in 4 ways any lot can be accepted. If you have 3 defect, then also it is accepted. If you have 2 defect, then also it is accepted. If you have 1 defect, then also it is accepted. If you have 0 defect, then also it is accepted. So sum them. So this probability has come out to be 0.9967. That means very high probability is there. So like that we can do that. So this was only for P is equal to 0.01. Now if P keeps changing, that means this was for 1% defective. Suppose the defective was 2%, then also we can do similar calculation. Only change will be what? Instead of 0.01, I will be putting 0.02. Here also I will put 0.02. So these two changes, 0.02 here, 0.02 here, other portions of the formula remain same, everything remains same. If I want to make 3% defective, then instead of 0.02 here, I write 60 into 0.03, and then e to the power minus 60 into 0.03. So like that we will be doing that. So and corresponding probabilities I will be evaluating. So I got a table type of thing, that when percentage defective is 1, then NP becomes, only NP gets changed, that becomes 0.6, and PA becomes 0.9967. If percentage defective is 2, then PA becomes 0.9662. If PA becomes 4, the percentage defective becomes 4, then PA becomes 0.7784. If it becomes 5, like that, and up to 15 I have calculated. You can calculate as much as do that, and then I can represent all these in the form of a graph actually. I can, on x axis I can write the percentage defective, and on the y axis I can put the probability. So it is, we have got something like that, that suppose this is 5.1 and 0.630, 0.36, this one suppose here 5, okay, 5% defective, what is the probability? 0.642. So maybe that this one n is equal to 60, this type of curve has nicely come. So this means that your lot will be accepted with what probability? That actual percentage, suppose your actual percentage defective is something like 5.1. In that case, probability of acceptance will be 0.63379, okay, that type of thing. Now if we want this type of situation, that somebody wants that 5.1 is a very sacrosanct type of thing, naturally that he wants that as soon as the defective becomes more than 5.1, in that case this should be rejected, and if it is less than 5.1, then it should be accepted. Then ideally your curve should be like this. You have this red, you just see that this is rectangular type of thing, and it is going like that with red line I have shown. So what does it mean? That it means this type of curve you need, that immediately suppose defect is less than 5.1 percentage, then lot should be accepted. So that probability should be 1 throughout, and then it will have sharp demarcation. If it is more than 5.1, then it should be rejected. Suppose we want to have that, this is very clear cut and very distinguishing type of thing, but it is not possible. It is theoretical only, we know that it is not possible. See, it will be a smooth curve or something. So you have to decide that what type of thing, which curve will be better for me, that type of decision you can take. If you take this type of curve, that you take n is equal to 60, then even if you have got 10% defective, even then you are having substantial that probability. So you don't, so that means you are at risk. So therefore what you do, that you have to say reduce something. So what you have to do, that suppose you take n is equal to 100 and other things remain same, that acceptance number is only this one, but n has become 100, that means sample size has increased. So you see that whole probabilities will change. Now the probabilities will be lower, because in 60 finding out 2 defects is very difficult, but in 100 you can easily find out, because bigger size is there, so there are more chances, more defective items will be there. So naturally it will be lower, and if you calculate, it will be this type of curve. Even then, if you feel that at 10% it is much more, then you can even increase, you can put n is equal to 150, and if you do n is equal to 150, then you can see that at 10% defect it is almost 0. So there is some small probability that even if you are having more than 5.1 defect, even then it is coming, that is one thing. So but more or less it is okay. And here, but what happens, that supplier or manufacturer may complain that this is very stringent, because what happens, he will say, sir, my defect was 3% also, but my probability of acceptance is actually very small, it should have much high, but it is probability, that means something like 65% or something. So what to do that? So both the parties have to agree that what type of sampling plan should be there, then we make the compromise. So that is what I am just showing, that effect of the sample size. Okay. So here another thing is that suppose sample size remains same, if you put if you increase the acceptance number, suppose C is equal to 3, I said that acceptance number is 3, but I can say that no, my sampling plan is same, that but my acceptance number will be 2 only. That means moment I will be getting more than 2 defects, I will reject your lot. In that case, again the probability of acceptance will become lower. It will become like that. And then similarly, if I say no, I am even more strict, if I expect only 60 pieces, that but if there will be more than one defect, then I will reject. Then naturally this type of curve will come. So we can decide. So two things you can manipulate, that number of samples to be inspected and number of acceptance number. Based on that you can take the decision. So as I discussed that both the parties will fight, because this fellow manufacturer would like that my lot should be accepted, and purchaser will be very strict if he will ensure that if there are high number of defects, then lot should not be accepted. So naturally, but they make a compromise and they do that thing. So naturally both the parties are ready to accept some risk. So what are those things? We say producers and consumers risk. Purchaser is called consumer and manufacturer is producer. So a producer always tries to produce the products of high quality in the hope that such a lot is accepted by the customer. The acceptable quality level is regarded as good level of quality. That means he says that he makes some acceptable quality level, both the parties agree to that and they think that it is good level of quality, which is called AQL. AQL means acceptable quality level, say 3%. Okay, suppose 3% defective is acceptable for me. So AQL represents the maximum proportion of defectives which the consumer finds definitely acceptable. Okay, so it always finds acceptable. However, an ideal sampling plan that discriminates the good lots perfectly always from bad lots is rare, because that type of thing you cannot make, as I said, that this type of curve. Suppose acceptable quality level is 5.1%. So before 5.1 you should have probability of acceptance 1, after that it is 0. This type of thing is simply not possible. So what do we do that? Hence there always remains a risk that a good lot will not be accepted. The producer's risk, we denote it by alpha, is defined as the probability that lots of good quality level AQL will not be accepted. That means even though it was a good quality, it will not be accepted. That means it got rejected. For example, alpha is equal to 0.05 means that in the long run about 1 in 20 lots will be rejected, even though the lots are coming from a process controlled at AQL level. And consumer's risk, also known as type 2 error or beta risk, is the probability of a bad product being mistakenly accepted and reaching the consumer, potentially leading to financial, reputational or even safety issues. So that is beta risk. So we have to say, and about consumer's risk, we sometimes define lot tolerance % defective is the dividing between good and bad lots. So since lots of this quantity level is regarded as poor, it is expected that the probability of accepting such a lot is low. So he will fix some lot tolerance % defective. However, if the consumer accepts such a lot, entire loss has to be borne by him. Consumer's risk, denoted by beta, is the probability that lots of quality level LTPD will be accepted which otherwise should be rejected. Suppose beta is equal to 0.1 and LTPD is 2.5% defect. It means that the consumer will most likely accept 10% of the lots containing 2.5% defectives, because probability is 0.1 of accepting that. Now what about average outgoing quality? A rejected lot is subjected to 100% inspection and all defectives found are replaced by good parts. This results in a lot free of any defectives. If a lot is accepted by sample, then there is a risk that some defectives have passed. The AOQ represents the average % defective in the outgoing products after inspection. So it tells that what is the average outgoing quality. So the number of defectives in the lot after n items in a sample has been passed is p into n minus n, because I have already, there was a lot of n, but then I have inspected n items and percentage fractional defective was p. So basically the number of items is Pn minus n. Note down, I am not doing P into n. Actually P into n were there, but when you did sample inspection, then even if there was some defective item, naturally that has been removed or repaired. So you have effectively number of defective items which will be left, they will be Pn minus n. This is multiplied by the probability of acceptance. It provides the outgoing quality of a lot. That means mathematical expectation, because quantity multiplied by probability. So Pa into n minus n into P. Hence the AOQ is this number divided by the number of items in the lot n. So average outgoing quality is Pa into P, n P into n minus 1, Ppn minus 1 into Pa, and divided by n, fractional form, multiplied by 100. So it will be in percentage AOQ. So if you see that if you plot this quantity with respect to actual percentage defective P versus AOQ, now P, although in this expression you are getting P, but Pa is also dependent on P. So you will get this type of graph, okay. That means actual percentage defective increase, then average outgoing quality level increases. That means more defective chances are there, but after a time it saturates and it comes down. Why it happens like that? Because if defectives will be more, then there will be more chances that it will be caught, and then you have to do inspection, it will be naturally caught and done inspection again, and that is why this one. So you just see that this peak in the curve is called AOQL. That means average outgoing quality limit. So AOQ curve for n is equal to 1000, lot size 1000, n is equal to 60, C is equal to 3, AOQ is equal to this much, and this one. So this is basically this one. Now we have told about that single sampling plan. In such a plan, only 3 numbers are specified, that is lot size n, sample size n, and acceptance number C. For example, n is equal to 1000, n is equal to 60, and C is equal to 3, means that the sampling plan consists of 60 items from a lot of 1000. The lot is accepted if the sample contains more than 3 defectives, otherwise accepted. But we can have double sampling plan. In a double sampling plan, the decision on acceptance or rejection of the lot is based on 2 samples. This type of decision becomes important when the sample taken for inspection is neither good nor bad enough. So the procedure of a double sampling plan is illustrated like this. Suppose we have n is equal to say 600, and we take first sample is n1 is equal to 30. And C1 is equal to 1, that means you accept the lot only if the defect is not more than 1 defect. And N2 is equal to, suppose we take 45, that means second sample I can take, which will have 45 components, and in this I fix C2 is equal to 3, that means acceptance number for the 2 samples combined together should not exceed 3. So that means this is 1 and this is 2 and this is 3, like that. So that means already suppose you have got 1 defect, suppose you have got more than 1 defect, suppose you have got 2 defect, then naturally you will go for the second inspection. In the second inspection, if the defect will be more than 3, that means you can expect only 1 defect in the second sample, because it is whole thing is a combined one. Okay, suppose you have, if you have got 1 defect here in except sample 1, then you can afford 2 more defect in sample 2. But in that case this will be, so here mostly you will go for second sample when the defect C1 comes out to be, let us say this number comes out to be 2, okay, or it may come 3 also, then also you can go for defect. If it is 2, then in the second sample you can afford only 1 defect. If it is 3, then second sample you can afford only 0 defect. So take a first sample of 30 items from a lot of 600 and inspect. Accept the lot on the basis of first sample. If it contains 0 or 1 defective, then no problem, then you pass the lot. Reject the sample if it contains more than 3 defectives, naturally then also you reject because no need to go for the second one. But if the first sample contains 2 or 3 defectives, take a second sample of 45 items. Accept the lot on the basis of first and second sample combined. If the combined sample of 75 items contains 3 or less defectives, then you accept, otherwise reject the lot on the basis of combined sample if the combined sample of 75 items, 30 plus 45, contains more than 3 defectives. So you can find out the probability in this case also. Suppose you have 0 or 1 defective in the first sample without taking second sample. In order to calculate the probability of this lot, assume that population is 5% defective. Suppose number of defective items will be 30. The probability of 0 defectives in the first sample is PA 0, 30 into 0 point this one and 0.223. Probability for 1 defective in the sample, this is PA 1. So PA 1, so instead of 0 we put 1 and this comes out to be this one. Hence the total probability of acceptance of 0 or 1 defective in the first sample without taking second sample is 0.558. And now suppose 2 defectives in the first sample followed by 0 or defective, 1 defective in the second sample. Then you have now for the second sampling plan, now you have only 570 in the lot since 2 defectives are already in the first sample. Hence the number of defectives left will be 30 minus 2 because there are 30 defectives by percentage wise, then 28. Hence percentage defective has changed slightly. Hence the probability has become, that is, first is that probability that there are 2 defectives in the first sample. So this is 0.05, but multiplied by 2 situation, there are 0 defectives in the second sample and there is 1 defective in the second sample. So here both the Poisson probabilities are written and this quantity comes out to be like this. So combine probability, another thing is that 3 defectives in the first sample followed by 0 defective in the second sample. For that, since 3 defectives are already present in the first sample, hence the number of defectives left will be 30 minus 3 is equal to 27. Hence percentage defective will change again slightly. Probability will be 30 into 0.05 into E minus this much multiplied by, this is only accepted if there is a 0 defect in the second sample. So this probability comes out to be like that. Then the total probability of acceptance of this lot is actually this much. Okay. So this is what? Then one small point I can tell about acceptance sampling by variables. In that we will not speak much, but we are telling that it is based on the confidence interval. Suppose we take that we measure something, we decide that suppose this is the mean value and this is the standard deviation, and we say that I can assume that this much mean and this much standard deviation is acceptable for me. So x plus minus k sigma gives you confidence limit. Okay. If the things are within the confidence limit, then you can pass it, otherwise you can fail it. Okay. So this much only today for acceptance sampling. Okay. Then we will discuss more. Okay. Thank you.